Okay, welcome to another talk of the virtual seminar of Geometry with Symmetries. In this opportunity, we have the pleasure to hear Silvio Reggiani from Universidad Nacional de Rosario in Argentina, that he will speak about the geometry of the sedenions, zero divisor. Thank you, Silvio.
Okay. Thank you for the introduction, and thank you, Emilio, also for the invitation to participate in this very beautiful seminar. So, in this talk, I want to talk about some homogeneous metric that appears naturally on the sedenion zero divisors. It's a problem that I've been studying for some years now. So, this is what I know so far. In order to define the sedenions, we have to define or recall the definition of the Cayley-Dickson algebra. The Cayley-Dickson algebra, remember that they are constructed recursively, starting with the real numbers, and in each step you double the dimension, and the multiplication and a conjugation are defined in this way. So, for example, the first Cayley-Dickson algebra are very well known, are the real numbers, the complex number, quaternion, and the octonions. And the sedenion algebra is the following one, which has dimension 16. Well, some elementary algebraic properties of the Cayley-Dickson algebra are the following. The first two are commutative. Then you start to lose some properties. They are associative only up to the quaternions. They are alternative up to the octonion algebra. Sorry, I don't know how to here. Oh, well, no problem. Can you see the cursor?
Yeah, we can
Yes,
see.
yes, we see.
Perfect, perfect. Well, I was saying that they are alternative up to the octonion. This is, if you don't know, this is the definition of the alternative property. And some property that holds for all n is that the Cayley-Dickson algebra are flexible, which means this some kind of less restricted associativity, and they are power associative. In particular, with this, we can define the exponential map and some other power series. And the other thing that I believe it is well known is that the algebraic structure of the Cayley-Dickson algebra is related to the geometry of the Euclidean space, because the inner product is given in this way. We have this property to compute the norms. We multiply an element by its conjugate, but in general, we do not have the property that the norm of a product is the product of the norms. Well, the other very well-known fact is that only the first four Cayley-Dickson algebra are division algebra. After the octonion, we have a zero divisor, which is the main topic of the talk. So, about the automorphism group, for n greater than or equal to 4, we have this relation between the automorphism group. The automorphism group of an equals the automorphism group of an minus 1 times this 3. This is the symmetric groups in 3 letters, and it is correspond to the new imaginary units that are introduced by the Cayley-Dickson process. So, in particular, we have that the automorphism group of an is the automorphism group of the octonion, the Lie group G2, times S3 to the power n minus 3. In particular, well, we have that the dimension of the automorphism group is always the same after the octonions. So, automorphisms leave the zero divisors invariant, and, well, the topology and the geometry of the zero divisors becomes more complicated as the codimension of the automorphism group increases. it is says sometimes that Cayley-Dickson algebra lose properties when you iterate the process, but it's not so clear what properties do you lose after the sedenions because they are all non-associative, non-alternative. But I think one nice way to see is that which is worse with the process of the Cayley-Dickson construction is that the topology of the zero divisor becomes more complicated. So, the zero divisors. We can think of the zero divisor of the Cayley-Dickson algebra in essentially two ways, and every one of these presentation, I think, has a geometric meaning, at least for the sedenions. The first one, we can think of the zero divisor of pairs of two elements that multiply to zero. It is usual to take the elements of the same norm, and this square root of 2 is just a normalization factor, but the important thing is that the two elements belongs to the same sphere. If we take the first coordinate, we have this other way to present the zero divisor. I mean the elements in a sphere whose annihilator is non-trivial. It is the same to consider the first coordinate or the second coordinate because you can prove that left zero divisor are also right zero divisors. For the larger Cayley-Dickson algebra, we can refine this description and we can stratify the zero divisor according to the dimension of the annihilator. Well, this CD of K is the 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 zero divisor whose annihilator has the dimension K, and this proposition describe which values of K are possible. I mean, such that we can find actually some zero divisor with this dimension, and it turns out that all the values have to be a multiple of 4 and are bounded by these numbers. But for the sedenion algebra, this is not a problem because all the zero divisors are in the same CD4. So, the topology of the sedenion zero divisor. I think it was Moreno, one of the first to study the zero divisor from this geometric point of view. And well, you can describe the structure of the zero divisors as a principal bundle with total space, this Lie group G2, and the base is the Stiefel manifold of of the two frames in R7. And the structure group is the sphere. This is the sphere. You can think of this as the spheres in the annihilator. So I will go with the details about this identification, but this is like the main ingredient. So the proof of Moreno, it is not so easy to understand, at least to me, but later we can do a more simple proof using this result that will be important later. An element in a sedenion is a zero divisor if and only if the following holds. If we think of a zero divisor as a pair of two octonions, then the two elements have to be imaginary of the same norm, and they have to be orthogonal inside the octonion algebra. So, with this proposition, we can explain a little bit better the previous identification. Well, the zero the divisor as pairs uh, are identified like with the Lie group G2. Well, this is essentially one of the main parts of Moreno's proof. You can prove that the automorphism group, the connected component of the automorphism group of the zero divisor acts simply transitively. In order to get the identification with the Stiefel manifold, we do the following. If we think of an element of G2 as an automorphism of the octonions instead of the sedenions, well, then it is completely determined by an orthonormal three-frame of three imaginary octonions, such that the product is orthogonal to of the two first is orthogonal to the third one. So the projection map is mapping the first two, I mean dropping the third coordinate. This induces the diffeo between the zero divisors and the Stiefel manifold in the second version with one coordinate. Okay. One remark is that the above proposition also gives a criterion to check for simple zero divisor. I mean, like a simple combination with sums of the element of the basis. For example, you can check that this E1 plus E10 is a zero divisor, and also is this E4 minus E14. There are only 84 pairs of this form, which are zero divisor, and they are called the standard zero divisor. I have here a table of all the 84 standard zero divisors, don't worry about it. Of course, notice the following. They are algebraically equivalent, since the automorphism groups is transitive in the zero divisor, but I highlighted in red some zero divisor that I will use later to make some computation of the geometric tensors of the metric, of the homogeneous metric, that plays nicely with a specific basis of the algebra of G2 that I will give in the next slides, I believe. So, let's talk about the geometry of the sedenion zero divisor. The first version, remember, with pairs of elements that multiply to zero, lives in a product of two copies of the sedenion algebra, which you can identify with R to the 32. And, well, the metric is the usual submanifold metric. But the important thing is that this Lie group G2 acts transitively and also acts isometrically. So the matrix is homogeneous under G2. The action is the usual. We identify G2 as a subgroup of the automorphism. Well, I mean, it's in SO7, but you can look at it inside SO8, and you include it in SO32 with four copies diagonally, the same matrix in four places. So this is the transitive isometric action. So the metric of the zero divisor is then just a left-invariant metric in the Lie group G2. In order to describe this metric in the Lie algebra, well, we have to choose an origin, and in order to do computation simpler, we have to take a specific standard zero divisor that is one of the highlighted in red in the previous slide. Well, let's do some of this computation, or at least let's write the general form of the metric. Well, we have that the Lie algebra of G2 is the derivation algebra of the octonions, and we are identifying this Lie algebra as a subalgebra of SO4. We consider this the invariant metric with this scaling, and we have the following orthonormal basis. The explicit formulas are not here, but there are in the preprint, so it is not important to see the matrices, but the important thing is the following. This basis of G2 has the following property. The first three elements generate a Lie subalgebra isomorphic to SO3. The second three elements are another SO3, and this SO3 commutes, and they give the maximal SO4 inside G2. Okay. The first subalgebra is the one because these are not equivalent. The first one is the one that acts trivially in the quaternion subalgebra. This is the usual quaternion subalgebra in the Cayley-Dickson construction. You start quaternion, octonions, sedenions. Well, the case zero acts trivially in this copy of the quaternion. The other SO3 leaves this invariant, this copy of the quaternion invariant, but the action is not trivial. So this SO4 preserves the decomposition of the octonion as the orthogonal sum of the quaternions and the orthogonal complement. Well, maybe this is well known to uh, some of you. This is the classical way to describe this exceptional symmetric space G2 mod SO4 of quaternion subalgebra of the octonion. This is a symmetric space with the normal homogeneous metric. So let's recall
Silvio,
the definition of naturally reductive space. A
Silvio,
homogeneous Riemannian space. It's said to be naturally reductive. We have a reductive decomposition, G equals H plus M, with this property. Okay? So it is known that naturally reductive space are very important. They have distinguished geometric properties, and well, as particular cases, you have the symmetric spaces and the isotropic reducible spaces, normal homogeneous spaces, etc. Well, I will have to use this. This is a very well-known theorem by Datry and Sealer, which characterizes the naturally reductive spaces on compact simple Lie groups. The construction is as follows. The naturally reductive metrics in Lie groups, you have to, you choose a compact subgroup of G, but you let this subgroup H act in by the other size. And well, this you decompose the Lie algebra of H into the center and these simple ideas, and you can modify the metric in the simple ideas by rescaling the invariant metric. You can use the different factor for the scaling, and you have to rescale the invariant metric also in the orthogonal complement of H, and in the center you can put anything. So these are all the naturally reductive metrics on compact simple Lie groups. Well, in our case, we have that the submanifold metric is naturally reductive. And well, it is naturally reductive with respect to G2 times this SO4. It has positive Ricci curvature. And also we can see that the sedenion zero divisor is the total space of a Riemannian submersion over this exceptional symmetric space. And the fibers are locally product of two spheres, but with different radius. Well, this is maybe the first interesting result. The proof is very simple. We use that receiver, and we have to write down the metric in the Lie algebra, which has the following form. In this case, sorry, we have to, this H is SO4, so there is no center. We have the two ideals, the SO3. Here we have the invariant metric, and we have the invariant metric, but rescale, and also the invariant metric in the orthogonal complement. So the metric is naturally reductive with respect to this presentation group. We can compute the Ricci curvature using the Sealer, or we can compute explicitly the Ricci tensor and see the other path. Well, this is about the geometry of the zero divisor as pairs. Now let's say something about the zero divisors as the Stiefel manifold. So in this case is pretty similar. We have that G2 acts transitively and isometrically, and the isotropy is the sphere, is the group SU2. So we have that the submanifold metric of the sedenion zero divisor in this presentation correspond to a homogeneous metric on the Stiefel manifold V27, which is only invariant under the Lie group G2, because the full orthogonal group doesn't live invariant the zero divisor. So we can reduce this is just a curiosity because in this work we are studying the intrinsic geometry, but we can reduce the codimension, and actually the geometry of the zero divisor is the geometry of an hypersurface of a product of spheres. Well, to study the geometry, we need a reductive decomposition, which is given by. Remember, we have the isotropy here is the SO3 corresponding to the K0. So the reductive complement, we can take the orthogonal complement with respect to the Killing form, to the invariant metric, and it has these distinguished subspaces. This M0 is the other copy of SO3, and these are other subspaces of dimension 4. So if we write down the metric, we have the following formula. It is not so nice as in the previous case because we don't have here a multiple of the Killing form in the subalgebra M0, but well, at least it's a diagonal metric. So, well, before giving the theorem, this is an experimental remark. If you take the planes associated with this basis of M, well, you have that I mean the canonical planes. You can compute the sectional curvature, and almost always is non-negative, except for the first plane. This basis is or this plane. Well, I mean the basis is not orthonormal with respect to the metric, but is orthogonal at this. I will go back later to this point. Well, before the main theorem, let me recall some fact about Einstein homogeneous spaces. Well, everybody knows a Riemannian manifold is Einstein, is the rigid tensor, is a multiple of the metric, and Einstein metrics are very, very interesting. They are rare and have distinguished geometric properties. Well, here we are interested in the existent problem in the compact case where this C, which is the Einstein constant, is non-negative. So, some results that are relevant to this talk. Well, this result by Bohm and Kerr says that for dimension at least 11, if you have a compact, simply connected homogeneous space, G mod K, well, it admits a homogeneous Einstein metric, which is not necessarily invariant under the whole G. You can have a smaller transitive group. And this is not true for greater dimension. In this work of Wang and Sealer, there is an example of a 12-dimensional compact homogeneous space which do not admit any invariant Einstein metrics. Namely, the space is this SU4 over SU2, but this SU2 is not the standard one. So, let me also recall some facts about Einstein metrics on manifold, which are the underlying manifold to symmetric spaces. Well, of course, the symmetric metric is Einstein for irreducible symmetric spaces. We show the result by Datrias and Sealer. Study this problem in compact groups. They are studying naturally reductive Einstein metrics. Naturally reductive Einstein metrics in compact D groups are covered in this paper. Also, there is this work by Kerr, where she gave the classification of Einstein metrics on compact irreducible symmetric spaces, which are not of the group type. So, completing the description started by Datry and Sealer. From Kerr's paper, there is one relevant example for the circuit of the tag, which is the Grassmannian of two planes in R7. She proved that the Grassmannian admit three non-equivalent Einstein metrics: the symmetric one, which is invariant under SO7, and two G2 invariant Einstein metrics. Well, Einstein metrics on Stiefel manifold are studied up to a point. recall the definition of Stiefel manifold is the manifold of or orthonormal K-frame on Rn. The extreme cases are the V1n is the sphere of dimension n minus 1, and the Vnn is the full orthogonal group, which correspond to symmetric spaces. And the one we are interested in is the two frames in Rn, and you can think of this as also as the unit tangent bundle to the sphere. The usual homogeneous presentation is this one, and results about Einstein metric on Stiefel manifold. We can recall this result by Seigel and also by Jensen, which says that there always is at least one SON invariant Einstein metric. Later, it was proved that this SON invariant Einstein metric is unique for the Stiefel manifold V2n. Also, in the work of Arbanito Yorgos and some collaborator, there are new examples of Einstein metrics and Stiefel manifold which are not of the Jensen's type. So, our result. Well, in the maybe you forget the definition, but in the sedenion zero divisor, we can modify the metrics in order to try to find some Einstein metric. So we change the metric on the Stiefel manifold like you do in the Hopf fibration to define the Berger spheres. We change the metric along a circle fibration with this parameter R. This, if you put, I think it was R 1/2, is the usual sedenion metric, metric on the sedenion zero divisor, but we change along this direction. See? And we call this Berger-like metrics because it resembles to the Berger spheres. Well, the main result maybe is this. You can compute the full isometric group of this Berger-like metric. It is always the isometric group, the connected component is G2 times a circle, and it's always this inside the diffeomorphism group is the same circle acting as isometric for all these Berger-like metrics. Well, we have something about the scalar curvature. It is positive for these values of R, and the notable fact is that there is an Einstein metric in this Berger-like curve, which happens precisely when R equals 5/9. So before giving this remark about the proof of the second item and the third one, you can do it by direct computation. To compute the isometric group, you can use a result by Onischik that basically says that you can compare the isometric group with the isometric group of the normal homogeneous metric. It's always smaller, and well, these are computed in some all words also, but well, this is the full isometric group. So a remark about the Einstein metric is that this is a new Einstein metric because it is not a Jensen metric. Jensen metric have this form. You have to, in this case, you took a subalgebra. This is the SO3 corresponding to the other factor of the SO4, and you put a parameter there, and you put the invariant metric. You leave it as it is in the orthogonal complement, and Jensen metrics appears for some values of this t. In this case, this is not a curve of Einstein metric. Of course, the values for the Einstein Jensen metrics are these two. So our metric is not Jensen because it is not a multiple of the Killing form in the complement of this SO3, and it is not obtained from the Kerr-Einstein metrics in the Riemannian because the metric of Kerr do not live via the standard projection. Well, we have our Einstein metric. This is we can study the stability of this new Einstein metric. Remember the stability problem for Einstein metric. Einstein metric on compact spaces are the critical points of the total scalar curvature, which is defined in this way. Sometimes this is taken over metrics of volume 1. This is the Hilbert-Einstein functional. But in the homogeneous case, we have the homogeneous version of stability. We can consider the normalized scalar curvature given in this way, and the stability problem. Well, I mean, G-invariant Einstein metric, a critical point of the normalized scalar curvature. The stability problem is, well, what is the nature of an Einstein metric as a critical problem, as a critical point of the scalar curvature? The stable metrics are the maximum of the scalar curvature. In our example, we have this Stiefel, the Stiefel manifold, and in order to study this problem, we need to describe the G-invariant metrics, and this is the part where the thing gets complicated because the isotropy representation has I mean, three copies of the trivial representation, and you have two copies of the quaternion, also two equivalent representation, and this makes that the dimension of the homogeneous matrix is 12, so the computation are very complicated. Well, we have this property. We have that it is not a very nice result, but every one of these Einstein metrics is unstable. The Jensen metrics are unstable, and our Berger like Einstein metric is also unstable. However, if you restrict the metric to the diagonal metrics, then it is a maximum of the scalar curvature. The first item in this theorem extend a result by Jorge Lauret, which says that Jensen metrics on compactly groups are unstable. Well, here there are some pictures. This picture is to understand why the Jensen metrics are unstable. This is the graph of the scalar curvature along the Jensen deformation. This is the family where the Jensen matrix appears here and here. And the first one is a minimum along this family, so it's disregarded as stable. And the second one here is a maximum, but it's not necessarily a maximum among all the homogeneous metrics. So we have to move in another direction to see that for example, in this diagonal direction, we find here our second Jensen Einstein matrix, and here is a minimum along this curve, so it's also unstable. And for the Berger-like Einstein metric, it's a little bit more complicated because we have to move along non-diagonal metrics. So the formula here is very ugly. This alpha is this number here. Well, this is not very important. You can see that it is not diagonal. And it's also complicated to verify this numerically. This picture is zoom in. So it is complicated because here we have the sedenion Einstein metric. And if you do not the computation carefully, you can miss this local minimum and only see this maximum. So this is the complicated part. But well, once you have the formation, you can disregard this metric as stable.
Silvio,
Yes.
can I ask you a question?
Yes,
Could you
sure.
please show me the previous picture? What about the maximum, the local maximum there? Isn't it an Einstein metric there?
No, it is not Einstein.
Okay.
But when you, for example, if you put this in the computer and you want to guess what about the Berger like Einstein metric, what you see with the standard scale is a maximum. Uh, 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 and
Yes. I
it's like
understand.
a very small local minimum.
Okay, thank you.
Well, let me see. Well, in the last part of the talk, I will talk about the non-negative curvature problem, also in the Stiefel manifold and the Berger-like matrix. So let us recall briefly about this problem. In, in a series of very celebrated works, there is the classification of homogeneous spaces admitting invariant metric with positive sectional curvature. These are very few examples, and such metrics are rare. If we relax the restriction and consider metrics with non-negative sectional curvature, well, these metrics are less uncommon, but they are still interesting. In general, you cannot expect to find a curve of this metric because the condition of non-negativity is not an open condition. However, there are not many general constructions to obtain metrics with non-negative curvature. You have basically these three. You can take product of metric with non-negative curvature. You can use O'Neill's formula and work with Riemannian submersion. For example, this is how you prove that the normal homogeneous spaces have non-negative curvature. And you can do this Chigger deformation, but you have to start with a metric with non-negative curvature. So the last result I will discuss is the following. These Berger-like metrics have non-negative sectional curvature in this range, with R between 0 and 4/9. This is interesting because they are not isolated example. This is like is a curve of metrics with non-negative sectional curvature, and it is related, of course, to the Berger spheres with positive curvature. Actually, if we realize the Berger spheres as the restricting the metric to the SO3 or the SU2, we have that the positive curvature appears precisely in this range. So, about the proof, well, we don't have a simple formula for the sectional curvature, like you have, for instance, for the normal homogeneous metric, or when you work with, for example, naturally reductive spaces. This is horrible, the formula for the sectional curvature, but we can use another technique. So in this case, we can use some very simple ideas from algebraic geometry and some ideas of convex optimization. So let me say something about that. Well, this is the something about the proof. This is not a brute force attack, but we have to study the sectional curvature in some way. So we will study the sectional curvature function. This is the sectional curvature without normalizing. We have 11 variables for the first coordinate, other 11 variables for the second, and this is a homogeneous polynomial, very complicated, but well, this is what we have to prove that is non-negative for R in this range. So one thing we can see from the previous formula is that if we fix all the variables, the map which sends R to the polynomial is linear, so it is enough to show that the extreme polynomials are non-negative. This F0 doesn't have a geometric meaning, it's like a formal polynomial, but it is well defined. What happens is that the metric degenerates when R equals to 0. But if we prove that these two are non-negative, we are done. So instead of proving only non-negativity, we will prove the stronger fact that these polynomials are, which is called SOS polynomial, are polynomials that are sums of squared polynomials. the following result gives condition to a polynomial of even degree being a SOS polynomial. This is the version for polynomials of degree 4, but in these papers you can look to the general version. Well, we need to find a symmetric positive semi-definite matrix H such that our polynomial has the form where this X is the vector of the monomials of degree 2. So, in our case, we have an advantage because we can reduce the dimension because since these polynomials are a sectional curvature, not every monomial appears. In fact, we only have monomials of this type, x, y, j, k, l, where the first two index are between 0 and 10, and the other two are between 11 and 21. So we can replace the x in the previous lemma by this one, and this is significantly smaller. Then we have to look for this matrix H of size, symmetric matrix of size 143 instead of the original or the one that the lemma gives, that is a lot bigger. So we have to find these matrices. This alpha is just to indicate the value of R, 0 or 49, but what this means that we have to solve this problem twice. Solving this problem is in general very expensive from a computational point of view. So this is a typical case of a convex optimization problem where we can state as follows. This H matrix, you have to write it like some matrix A0 and this very large sum, where this A0 is like a particular solution of the system you're trying to solve, but only with a symmetric matrix. You don't worry about the semi-definite condition. And the other ones are also symmetric matrices. This is like a basis of the space of the solution to the homogeneous system. So if you have a solution, you have to you can write it in this way. In order to treat this problem, we can use some software. You can solve this problem numerically. If the problem is not too big, here it is crucial to pass to a matrix of dimension 143 because otherwise you cannot solve this problem with a computer. But using this software CBX OPT, which is a package of Python that is also available in SageMath and in SageMath, we can have a numerical solution. However, this solution is approximate because we are solving numerically, but we need an exact solution because we are trying to solve a problem about a non-negative curvature. So if the error is small, we can think that the solution, the polynomials are non-negative, but actually in some point it could be a very small negative value. So the output of this CBX OPT this is a very small slide, but it's something like this. Well, the idea here is that you get a lot of entry with very, very small numbers that, well, you have to like guess where there are zeros in the matrix and where you have something like this, for example, 0.4999. Maybe in the exact solution there is 1 over 2 and something. So you can make some programs to make this rounding argument work. So in order to get the exact solution, we round all the zeros, and then you get a lot of places, but not so many, so that you cannot propose an exact solution. There is no way that I could make the matrix in a slide, but at least let me describe the solution like this. For example, for the F0 polynomial, we have these entries. In the place ij, we have the value a, and this entry could only be, here it is, 1/2, -1/2, 1, -1, 2, or -2. And this is the how many places you can find a 1/2. There are 256 places, 34 places for the ones and -1, and you have mostly zeros. In the other case, it's pretty much the same. Again, you try to guess what exact rational number is in the place where you clearly have something uh, non-zero. So you propose the solution. This is easy to check that they are exact solution that satisfy the system and they are non-negative, and so you're done. You have the f0 and the f4/9 are sum of squares, and all the polynomials in between are non-negative. One last remark is that this doesn't prove that the other fr are sum of squares. From the geometric point of view, it is irrelevant because we are only concerned with the sign of the sectional curvature, but maybe it is interesting from algebraic geometry point of view. I don't know. This is only a question that I stop studying here. So, well, that's it. Thank you very much.
Thank you very much, Silvio. Very nice talk. Are there questions or comments?
Hi, this is Wolfgang. I had some questions.
Hi.
I couldn't see your slides for some reason, but I know what you're talking
Oh,
about. So anyway, so you have this 12-dimensional space of homogeneous metrics, and
yeah.
are your solutions explicit of the Einstein matrix in that space? And do you find all of them?
No, I couldn't find all of them. I only got this new metric by almost by chance. It is a very hard problem to, at least with the tools I have, to find all the metrics in the space.
Are they explicit or numerical? I didn't see the slide.
Explicit. This one are explicit.
Oh, I see. And you found
Oh,
them by only guessing, looking only at diagonal metrics, or making some kind of guess, or what? How did you find them?
well, I lose the PDFs.
I can't see it anyway, so don't worry.
Yeah. Okay. The way I found the metric is I wrote down the explicit metric for the sedenion submanifold metric, and then I noticed that if I perturb this parameter in this direction, I will call this a Hopf fibration, but also maybe it is not a proper Hopf fibration. And changing the metric here, I got a family with a non-negative sectional curvature. Maybe the second theorem was the first one which I obtained. And then experimenting a little bit, I compute the Ricci tensor, and here I could see this Einstein metric in this parameter 5/9.
I see.
This is not one of the metrics with non-negative curvature. It's uh, farther,
I
from
found
the
it,
sedenion metric.
I found it interesting the way that you prove it doesn't one layer curvature. That's is that a method that works for any metric
Sorry,
or
I didn't
specialty
hear the
examples?
question, the first part
Oh,
of the question.
the method how you proved it has non-negative curvature sounds very interesting. Is this
Uh,
applicable to any metric or only special for your metrics?
I think it could be applied to other metrics or other homogeneous metrics, but yeah, I didn't see in many differential geometry papers this method. It was commented by a colleague from the algebraic geometry group, but they try things like this all the time. They use some software to get a numerical solution, and then they guess if they can find an exact solution to solve this problem of SOS polynomials. It is not unusual in other areas.
I see. But in general, say if you have even a curvature tensor on a vector space, to see whether it has non-negative or positive curvature is a difficult problem.
Yeah, yeah. I believe that you can try this method in other cases, but I'm not sure if it will work or not. Probably in most cases it's useless, but I don't know.
There's one other method I know how to prove it has non-negative curvature, where you the Thorpe trick, where you add a four form. Do you know how that works, and did you try that?
I didn't know this trick.
So if you add a four form to the curvature operator, then it has the
Okay.
same section curvature, and that then
Ah,
becomes a symmetric matrix. If that symmetric matrix is non-negative, then you know the section curvature is also non-negative.
okay. I didn't know that. Maybe it is related to what I did.
Oh, that would be interesting. In general, finding the four form that is
Yeah.
appropriate can be difficult, but that's how I proved, for example, that some new spaces had positive curvature by using this kind of Thorpe trick.
Okay. That's very nice. Thank you, Paul.
Sure. Very nice talk. Thank you.
Thank you.
So I have a question
Okay.
about
Yes.
the metric when it's got non-negative sectional curvature.
Yeah.
Uh, does it's still is it Ricci positive in those cases still?
No, not in all cases.
Okay.
But I cannot remember now, but it is in the preprint. Sorry. Uh, but it is computed there where in the cases where it is Ricci positive for all the curve.
Okay. Thank you.
Thank you.
More questions? I have another question. And by the way, we are now seeing again the slides. Did you use in some essential way that the space where the algebraic structure of sedenions, did you use in some way, or you can find the new Einstein metric and everything only with compact
I
diffusion?
am well. Actually, this is the thing I didn't like completely about the result. It could be nicer if we use the structure to compute some geometric tensor, but I I think that I was more comfortable to working with an isometric action and putting some reductive decomposition. But the maybe the history of the problem is that I knew this paper, or I read this paper of Moreno, and he proved that the zero divisor are a Lie group and there are homeo to Lie group, but actually they are diffio. And well, the next obvious question is that the submanifold geometry correspond to the invariant metric on G2, and this was the initial problem. And well, this is false, obviously, but then uh, making some experiment, they appear these interesting examples. But yeah, it would be nice to have an algebraic description of the geometric tensors.
Or extension to another Stiefel manifold, right?
Yeah, this is for the students.
Okay, is there the last question? Okay, if not, we thank again Silvio. Thank you very much, Silvio. Very nice talk.
Thank you. Thank you.